Welcome to the 2002 crash course. So it will be Johnny and myself teaching you guys today. If you guys have any questions at all, please feel free to ask. We have quite a bit of time, so if you don't understand anything at all, please let us know and we'll try our best to answer those questions. Yeah, we can do that now if you want. Before we start, Johnny just has a little bit to say about PDC, which is coming up very shortly.
Which will
PDC,
Henry? Oh, okay. Yeah. Well, okay. So PDC. PDC is a camp that's coming up in September. It stands for Professional Development Camp. So what that basically means is it's a 3-day camp for 2nd, 3rd, and 4th years. The aim of the camp, I think, is to professionally develop ourselves so that we're ready to go into the workforce. So what that means is that we're doing sort of resume writing workshops, cover letter writing workshops. We're going to talk about job interview type stuff. We're also going to have graduates that are currently working in industry, and they're going to basically advise you on what their fields of work is like. So I don't know if you guys are aware of the different areas of civil and environmental engineering, but there's different sort of sub disciplines you can go into. So we're going to have representatives from all those areas, and they're going to basically help you through understanding what all that is. Now, that's the daytime activities. The nighttime activities is some really cool parties, some really fun activities, and it's basically just to give you that, university experience that everyone wants, right? So, okay, there was meant to be a QR code in the bottom corner, but this is the event. You can hit up the Facebook page on CVSoc's Facebook. There's also a link in CVSoc's Instagram. If not, you can DM any of us and we can help you out there. Sales are open week 3. So actually Iman's one of the coordinators, so and so am I. But yeah, it's gonna be a really good camp. Anyways, let's get started. I think we've gone a bit over. Okay.
Over to you.
Alright, so hands up who's actually started studying for this subject. Cool. Who understands what's going on so far in this subject? Alright, cool. Who doesn't? Who confidently put up your hands if you don't understand? Because that's the point of today. I'm going to help you through it. Okay, cool. Now, I think you guys have heard a few things about this course. It is notoriously really hard, and the reason for that is because it's basically 2 subjects merged into one. So there's a numeric stream and there's a statistics stream. Which means there's 2 lectures every week, and there's also 2 compulsory classes every week. So there's a stats class and a numerics class. And it's really important that you stay on top of it, because if you do what I did last year and you decide to go on world tour during term 2, you're going to fail the subject. So don't stress. We're going to do this together. We're going to stick to the plan, and we're going to try to stay up to date, and hopefully we'll all get through with our limbs intact and we're going to be good. It's not that bad. It's actually not that bad. All right. So let's start with week 1. So can someone give me a quick summary of what week 1 content was about? Who's confident enough to give us a little? Can anyone define what a numerical method is, or a numerical approximation is? What does that mean? Okay, so basically throughout our entire lives of maths, we've been talking about finding the exact value of things. So when we talk about exact value, we're talking about in calculus, integration, differentiation. That finds you the exact value of whatever you're trying to find. The slope of a curve, whatever it is. An approximation is basically a method that mathematicians use when they cannot integrate or differentiate an equation accurately to find an exact answer. So we can use different methods to basically go about that. And basically week 1 content it's basically introducing that concept to us, and introduces the Euler's method, which is approximating values based on boundary conditions and other values that you are given. So we're just going to go through the lecture example, and I'm going to basically use it to talk through how you can use MATLAB and how you can use Excel to go about this course, because the thing about approximating is that there's a lot of iterations you have to do to reach your final answer. So what an iteration is one calculation. Basically you have to do that calculation a lot of times. for your Richard final answer. A lot of the time it's a bit impossible because imagine you have to do like 100 iterations to get there. So this is why we use Excel, because you can just double click the cell and it just populates, or you can use MATLAB, which basically is like a coding language and it just does it all for you, and it's like super cool. So week 1 content. So in the lecture we went through an example which was basically the parachute scenario. So let's imagine we have like a parachute, and on that parachute is a person with a particular mass. And so if we draw this like a free body diagram, we're going to have a drag, basically a drag force, which is F, we'll call this Fu for F up, so the force upwards, which is, okay, my handwriting is really shocker, I'm sorry. So Fu, which is going to be minus CV. So the C in this case is the value, the constant value for drag, and V is the velocity force. Down, we're going to have our sort of weight force. What is it? Someone yell it out to me. mg, beautiful. So D is going to be mg. Okay, so we're going to take up to be negative and down to be positive because that's the direction we're going. So that means our total force, or our sum of forces, is going to be basically both of them. So Fd plus Fu, which is mg minus cv. Okay, so the point of this, or what we're trying to find, all right, is we're trying to find the velocity at a particular point in the fall of the parachuter, the person, the free diver. Okay, so in order to find that, we need to sort of differentiate the equation. So if we do that, we end up with dv on dt, all right, and that's going to bring us to F on m. So how did I get there? So if we look at Newton's second law, all right, what is it? F equals ma, beautiful. F equals ma, right? And acceleration is basically our g-force, right? And so that's going to give us F over m. Now, if we look at, in calculus, moving from displacement to velocity, then to acceleration, how do we do that? First derivative, beautiful. So that means that this is actually the first derivative, right? So the change in velocity over time. And if we look to here, that's like the same thing, right? So that's going to bring us to, if we keep going, right, and we sub in this F value into our dv on dt, I wish there was a way that I can like, okay. Does this work? Oh, okay. Okay, I'm gonna do this. Sorry, this is, can everyone hear me? I think everyone can hear me. Okay, so, where was I? Okay, so from there, what we can do is we can actually sub in this F value into our first derivative, and that's gonna give us dv over dt, right? Which is mg minus cv over m. And that's like our first step. Our first step is to find the first derivative. Now, I think, you know, so far it's not too complicated. I think everyone's following along. Is that right? I think maybe I'm going a bit too slow, but that's okay. So this is basically a differential equation, and so the point of it now, we're going to try to solve it. So, going about this, right? We what we want to achieve is basically a curve on a plane, a curve on like a chart, and then we want to find our particular, like our points at each time point. So if this vertical axis is our velocity, and the horizontal axis is our time, right? So v for t, right? We're basically, what Euler's method is attempting to do is to find the slope between 2 points to approximate the slope of the next point. Okay. So if we have our initial condition, right, so vi, and we have our initial time, and we know the time that we're looking for, so v equals I plus 1, we can approximate v for I plus 1. I don't know why I keep making that look like a t, but there we go. Okay, so how are we going to do it? So if we look at a line, so in Euler's method, this is, what's the equation of a line? Y equals mx plus b, right? So we're going to try to find an equation that kind of looks like this so that we can solve for it. So, all right, so the equation of a line. So from there, the slope of a plane, which is m, so m also is dy on dx, but in this case, it's dv on dt, which we already found to be here. It's also the slope of this line in there. So y2 minus y1 equals x over x2 minus x1, so rise over run. We can find that to be this. So vi plus 1 minus vi over ti plus 1 minus ti. Okay, so now that we have that, right, we can go back to our original equation, which was this one, and we can rearrange it so that it looks more like a function in terms of v for t. So how I'm going to do that, I'll just rewrite it. So mg on m minus c v for t over m. So these go away, and then it starts to look like this. Okay, the reason why I'm going through this is because I'm trying to make it look like what Elena goes through in the lecture, because she doesn't really, I feel like she speeds through a lot of it. And for me, especially the first time I was doing this course, I found it quite confusing. So this is basically just the thought process behind it. Like, don't think too much about it, but it's really just linking 2 and 2 together to come up with, is everyone finding this really easy so far? I feel like it's a lot easier than what it's made out to be, or what it's, at least I'm making out to be. Okay, anyways, is what it is. So if this is dv over dt, and that also equals this thing, then we can basically get like this equals this, and then we end up with an equation which is v ti plus 1, right, equals vi, or vti, as in like our first time point, right, plus g minus c on mvti outside of ti plus 1 minus ti. Okay, so all I did, I just made this equals this, and then I rearranged it to get this. So now what we need to start doing is we need to start iterating to find the velocity at a particular timestamp. Okay, so I think in the lecture example, they wanted us to find the velocity at 12 seconds if the dive is falling. Okay, so I'm actually going to solve this part on Excel, just because I don't really want to start punching into a calculator. Okay, so let's take G to be 9.81, right? Our C value, sorry, I'm going through this really slow. I'm pretty sure this is 12.1. Our V is the unknown. M, so the mass of the diver is 68.1, right? And our time step is 2. So if we look at the function again, one more time. So when I talk about a time step, I'm talking about the points on this axis and how many jumps we do. So the reason why that's important is because the distance between our jumps affects how accurate our approximation is. So if we look back to calculus, when we're integrating, so our dx, our distance between each column, the smaller it is, the more accurate our area under the curve is. Is that right? We can all agree on that? So this is kind of similar. So we want to make sure our steps are as small as they can be if you are coming up with the solution, but in this case, it tells us the step is 2, so we're just going to go with that. Okay, so these are just the conditions that are given in the question. By the way, I haven't worked any of this out. This is all given. Okay, so from there we're going to have 3 columns. So T, V, T, I, and V, T, I plus 1. Okay, from there we have our steps, which is 0 to all the way down to 12. Okay, our initial value that's also given in the question is that our velocity is 0, right? Because from timestamp 0, if we jump from like the first point, we're obviously not moving. And now this value, VTI, is basically this formula. Okay, so bear with me. I'm going to try really hard to like do this quickly. Okay, so this equals this plus this minus this over, oh sorry, why am I doing that? Over this, right, times this, times our time step. Okay, that's wrong. What did I do? Okay, this would be so much easier if I had my laptop here because I could just show you exactly what I've done. Man, this is so embarrassing. Okay, bear with me for a second. I promise I like know what I'm doing. I'm just having a bit of issues right now. Okay, so this plus G minus C over M, which is multiplied by our VTI, and that is again multiplied by our time step. Okay, fingers crossed. Everyone pray for me. Okay, oh, what the hell? It should be 19.62. Can anyone spot what I'm doing wrong? Just to save me time. No? Okay, well, anyways. I wonder if I can put this in the camera, just for the recording. But basically, you're going to end up with this. You're going to end up with a bunch of cells that basically lead you to your answer. I've highlighted the correct answer there. It's 50 point something. Yeah, go for it. Okay. Yeah, okay, I think we get it. I think we should just move on before I sweat some more. I'm like sweating so hard. Yeah, please.
I think it turns off every 2 hours. Yeah, that's why. Takes a second. Okay, now you won't be sweating balls.
Oh, so good, so good.
You're doing good.
Are you sure?
Sounds pretty good.
Okay, bring it back. It's all good. I think they can.
I think you timed it by B7. Are you meant to time by? Is that right? Time B7.
Mm-hmm. Hang on, can I have my notes back? Let me just have a look at that. Maybe I think what I'm doing wrong. I need to close this bracket as well. Okay, no, I'm not. Okay, this is really starting to piss me off. So B6, and that's in brackets. I know that. What the frick? Okay, there we go. So VTI. What's our VTI again? Oh, it equals this. So this equals this. All right, everyone better clap for me when I finally get it, because I'm like shitting my pants. No, that needs to move. And then this one stays, this one stays, this one stays, and the rest move. Lol. And the last one moves. Yeah, we did it. Okay, all right. Okay. I got there in the end. I'm kind of scared to open MATLAB now, because if I open MATLAB, we might have a similar situation. But you know what? She'll be right. Look, I have to say, the point of this right now, I'm not going to like tell you everything. Like, you're going to get a high distinction with everything I'm telling you right now. I'm just trying to show you like how you plug and chug with Excel and MATLAB to get through the course, right? Because like I went through this, now you guys will too. All right, I've got my MATLAB notes open, so I'll just. What's happening? Where's my actual notes? Okay, here we go. So, same thing. G equals 9.81. C equals 12.5. Right. M equals 68.1. And now dt is time step of 2. And then from there we've got, okay, who knows how to use MATLAB? Do I need to go through what everything means? Just quickly, do I need to go through what everything means, like all the notation of MATLAB? Does everyone know how to use MATLAB? You don't know how to use MATLAB? Okay, cool. Okay, so basically MATLAB is like a coding language. So when you write a letter or something, obviously you're establishing a variable, or you're establishing like a constant, and that, you know, you're saying that G is the name of that number. So we've got our gravity, our drag constant, our mass, and then this is our time step. So same thing to do what we did in Excel. Now what I'm going to do with T, I'm going to establish a vector of numbers, okay? And I'm going to do this by going 0, colon, dt, right, colon, 12. So what this means, okay, so T starts at 0, has a time step of 12, time step of 2, and goes all the way to 12. So how many numbers should I have there? Try again. 7, beautiful. So if I was to run that, there. So we've got our 7 numbers, they come out like that. Okay. Next thing I'm going to do, I'm going to establish our number of like times this equation happens. So NUMEL is like number of elements of T. Okay. And then from there, yeah, I think I already messed it up. Sorry. I need to just make sure I get the order right, because if I don't get the order right, it will scream at me. Okay, so what I'm going to do now, I'm going to establish our VI. So whenever in MATLAB you want to create a matrix of numbers, you first need to create the matrix, and then after that you need to populate using a loop. So who's done program before? Who knows what a loop is? What's a loop? Something that keeps going until it stops. So I'm going to give it a condition. So in this loop, it's pretty simple. It's just a for loop, and I'm going to establish that what my individual, like my first number is, and it's going to stop at n minus 1. So I established n here, and the reason why I said n minus 1 is because, as you can see, t equals 7, but I only want it to iterate 6 times. Okay. So if I just go back to establishing my variables, so VI, so this is my velocity vector. So VI is zeros for a size of n. No, just n. Okay, and after that, I want to establish what my first value for my velocity is, which is 0. All right. And then after that, I need to then, hang on, did I already do t? Yes, I did. Okay, I'm going to put that under it because, okay, there we go. Now I can write my loop. So here's what I'm going to do. I'm going to go v underscore I1, right? And then I'm basically just going to write that equation again. So vi plus g minus c over m times vi for I. Okay, and that's going to be multiplied by d underscore t, so by our time step. So if you look here, that's literally the same same value as the one I wrote, as the one we established in the notes. Okay, so what's happening here, I'm basically telling it that every time it iterates, so every time it does this calculation for whatever number it's up to, that's the value that it's going to input in my vector. So that's why I've put an I in there. So it's basically a function like f of x. This is just vi1 of I. Okay, so next line is going to be vi I plus 1 equals basically this. Yep. And then now I can just end it. Okay. All right, everyone pray again. Okay, this is going to happen a lot, by the way. You guys are going to get really frustrated using MATLAB. But, okay, what does it say? When calling a function in existing variable, use parentheses. I thought, what is that not related to? Okay, I think that was the problem. Did it work? Okay, it worked. How do I open it now? All right, there we go. It worked. So that's the actual answer there. So MATLAB's pretty easy. MATLAB is probably easier than Excel. Did that all make sense to everyone? All right, beautiful. So that's like the foundations of 2002. That's what you're going to be doing every week. It's just different formulas and different methods, and you're going to be applying those to MATLAB because there's no way you can do it 1,000 times. You're going to be telling MATLAB to do it 1,000 times. And MATLAB is great. I love MATLAB. I think it's really fun. So there we go. In my notes, I also transposed it because I was getting frustrated with looking at it sideways. So what you can do, you can go vi equals transpose. So if we go back to matrix, like algebra with matrices, if you transpose a vector, you're just making it like that, and then you're just turning it. So transpose vi, and that's going to give you this. Okay, I don't know why it didn't stop it. Okay, but the point of that, okay, the point of that is that it just turns it. All right, anyways, so that's that. We can now move on to like other things. I'm not going to go as in depth to the other stuff. I'm just going to show you the formulas and what everything means so that when Elena shows it to you in the lecture, you're not going to get like friggin' shocked. All right, moving on. Which one? Oh, all goods. Where is it? Oh, it's Leo, bro. Talks too much. What a yapper. Okay, week 2. I'm just going to do everything here. Is that okay? It's fine? Okay. So this is week 1. This one shall be week 2. Okay, so moving on to week 2. What is week 2 about? So week 2 is looking at more methods to approximate. So the first one we're going to talk about is called the bisection method. So 100% you guys haven't heard of this before, and if you have, good job, you're almost there. So the point of this week is to find the roots of an equation. So what is the root of an equation? Like if we look at the roots of a quadratic equation, what does that tell us? And what are those solutions? Where y equals 0, beautiful. So for example, if we had like some kind of, I don't know, the root is here, right? It's where y equals 0. So the bisection method, so this is the first one I'm going to talk about, bisection, right? Basically, you're going to guess two values. So for example, if I just guess a value is here and a value is there, right? We're going to keep finding the average between those until y equals 0. So as you can see, this value is going to be negative and this value is positive. Okay? So you're going to keep going about this iteration and you just pick the one that is positive and negative and you keep averaging them and it gets closer until it hits 0. So this is basically what it looks like. So if I was to make a formula out of it, right, our XR, like our new one, is going to be our lower X value plus our upper X value divided by 2. Okay, that's like just an average formula. Okay, so that's our step 1, to guess that's the case. So step 1, pick an XL and an XR so that F times XL and XU is less than 0. You want it to be negative because you want to have a positive and a negative value so you converge into a y equals 0. Okay. Step 2, you're going to estimate it using this, the next value, and then step 3, right? So if, so if f of xr, right, is less than 0, right, then you're gonna basically just swap it out. I've got a lot of notes here, but I'm not gonna go through it. I'll just go through an example and then I think that will make more sense. So the example that Elena goes through in the lecture is f of c equals 668.06 over c outside of 1 minus e to the power of negative 0.14 times c minus 40. Okay, so we're going to start with two random numbers. The two random numbers we're going to start with is, let's say our x upper is 15 and our x lower is 10. And if we compute both of those into the function, we're going to end up with f of 15 equals negative 0.3845, right? And f of 10 equals 11.4215. So as you can see, one of them's positive, one of them's negative. So what do we do next? You can tell me what we do next. Farhan, tell me what we do next. He's on his phone, sorry. Tell me what we do next. What do we do next? What do we do next? You told him though. Oh, no. Okay, anyways, does anyone know here? You know. Are you sure? I just said it. We'll find the average between the two. Okay, basically. Find the average between the two. So if I was to then just say what my XR was, I'm obviously not going to calculate it. I don't want to waste too much more time. But the average between those two is obviously 12.5. Right, it's just the average between the x values. Don't worry about the y values, the f of c values. They're just telling us where our point is, but we don't actually care about what the number is. We just want to know whether it's positive or negative. So then we go through it again, right? So because, so then we find our f of c value for here, so f of xr, right, which turned out to be positive, 4.9189. So because that one's positive, which ones do we get rid of? This one or this one? First or the second one? Beautiful, exactly, because it's already positive. So we're replacing it with a lower positive one. We're getting closer to 0. So then we go again. So our new f upper, or f lower, x lower. So xu is 15, xl is 12.5. Right, we compute those to get our next xr, which is going to be 13.75, right? So we're trying to find a new x value, and that's going to give us an f of c, which is 2.1351. Okay, now which ones do we replace? 12.5. So we're getting closer to 15. So if we were to look at this as on a plane, right? I don't know if this is the actual function, but let's imagine that this was our 10 and this was our 15. Right? We're getting closer and closer and closer and closer until we reach that point, okay? That's what the bisection method is. Any questions there? That made sense. Okay, I'm going to move on to the next one because I'm moving very slow. Okay, the Newton-Raphson method. This one's very easy. It's just a formula. Newton-Raphson. Okay, so this one is just xi plus 1 equals xi minus f of xi over f dash xi. So the different components of this formula, basically you got the function, you got the first derivative, and then you got your old x value, and all of that is to find your new x value. So the same as the Euler example, you can just plug it into either Excel or MATLAB, you'll get your answer. That's that one. And now the last one we're going to do for this week is the secant method, which is just another formula. Okay, the secant method. Don't ask me why it's called the secant method. You don't need to know why. You just need to know, learn the formula, which is I plus 1 equals xi minus f of xi outside of the change. Oh no, I'm not going to write change in x. I'm going to actually write it xi minus 1 minus xi, and then all that divided by x I minus 1 minus f of xi. So the difference between the second one and the first one is that in the second one, you're using previous values, right, to find the next value. So with these though, the thing about all of these all of these methods is that you're then going to be guided to find the error of each method. And so what I mean by error is that if we have our function, right, so let's say the real function might look like that, okay, and we're approximating with x values, it might do this. So you might get your first value to be here, your next value to be here, your next value to be here, next value to be here. And so the level of error you end up with is the distance between our approximated value and then this curve, which is our exact value, our exact curve. And so this distance here, this is our error. Okay? So calculating error with all of the methods throughout the rest of the course is always going to be very, very similar, unless otherwise. I'm not going to say it's always the same because I don't want to be liable if I say that and it's not the case. But basically, you're going to get the absolute value of the approximated value, right, minus the exact value divided by the exact value, right, times 100%. And this is going to give you a percentage of error. Okay? So this is going to be the case for all three of those methods. I know that for sure. I know that for sure. Okay? All right. That's week 2. It's not actually that hard. The hard part was me trying to show you how to do it because I can't do it. I will eventually do it. But anyways, minus technical difficulties. Does anyone have any questions so far? What do you reckon? It's pretty straightforward. Have I lost anyone? Yeah, go for it.
Is there a question how that works, like exam or quiz form? It's easy to remember the formulas. If you a sheet or you stuff on MATLAB, how does it work?
Look, from memory, I know that in the exam they're going to give you enough information so that you can do the question. Right? So if it's a crazy wacko formula, they'll just give it to you. But if not, you'll probably need to learn it. But from memory, I don't remember any of these particular methods being examined on their own. It's always coupled with something else so that it's doable. You don't have to memorize it, but you will be doing all these things enough so that you'll remember it to a good enough extent, right? You'll be fine. Don't worry.
All of your sorry, if I could just add,
yeah,
all of your quizzes as well will quiz you on these formulas and using the formulas in MATLAB. So by the time you get to the final, you're very well versed in Newton-Raphson and secant method, which more often than not they'll probably give you in the question. I think they gave it to us in our question as well. So even though it's closed book and they don't give you any lecture notes to go off, they'll always put it in the question if they think that you'll need it. Yeah. So you're not on your own. And we have group chats, so you'll be fine. Anyway, I'm joking. Yeah, don't do that. Okay, week 2's done. Any more questions before I move on to week 3 quickly? Week 3 is just matrices. It's really easy. Okay, I'm going to move on.
So the only thing you need to learn from week 3 is finding the determinant of a matrix. You can tell me what that means. What's the determinant? Yeah, basically. What does it actually mean? Like, does anyone actually know? And if you know, like, it's more about you than anything. Anyways, no. So, week 3. So week 3 is all about matrices. It's not really anything else. And like, it's not really examined too hard. So we'll all be fine. So the first thing we're going to talk about is this formula. So A times A minus 1 equals I. What's I? Yes, it's an identity matrix. So I of any size, we're just going to do 3 by 3, is like 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay? So it's like diagonal. It's a diagonal matrix. Okay. A to the negative 1 is... Oh, I'm losing people. It's the flipped version, and then A is our normal matrix. So if you go to MATLAB, right, you can find each of those values. You don't need to go through all the methods they tell you, but basically in the lectures, they talk about finding L and U, which is like the triangles. So L and U substitution. I don't know what it is, but let's go to MATLAB and we'll just do some cool stuff here. Okay, so let's make a matrix, a random matrix. I'm gonna say that it is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm just going to double check that that actually did what I wanted it to do. Okay, there we go. So we got a 3 by 3. Now, if you want to find the inverse, what is it again? Sorry, I just need to remember the function of the... Oh, okay. A to the sort of negative 1. I'm pretty sure it's just inverse of A. Please tell me that's right. Okay, so that's going to give you the inverted matrix. Okay, and if you wanted to find an identity matrix, there's a command for that too. Now, in the in MATLAB or in the lectures, you're going to be asked to find the L and U substitution, which is basically, well, like do an L and U substitution. I don't know how to do it, but basically if you want to find those matrices, it's just L and U, which equals LUA, and then this is going to give you those two matrices. Okay, so you're going to get your whatever that is, and then whatever that is. So have we seen these before? We've seen that before. I'm not going to go into detail of it. I'm just going to move on. Just remember this and this. We got it? Tell me. U. So U is the upper triangle matrix. So instead of populating the diagonal and below it, and then on the diagonal it's like 1, 1, 1, 1, 1, U is the upper side of that. Yeah, the top side. It's like the top triangle. Okay, that's week 3. That's literally week 3. Week 4. Oh my God, we're already 4 o'clock. I'm sorry, Akshara. That's on me. Okay, week 4 is great. Week 4 is all just integration, right? It's using the trapezoidal rule and the 2 Simpsons rules. So does anyone know about the 2 Simpsons rules? What are they? There's 2 of them. Yeah, they tricked us. There's more than one. So we've got 1/3 Simpsons rule and then a 3/8 Simpsons rule. So they've got their own formulas. I'm just going to write what they are. And then I'll try to show you my MATLAB code. And if that doesn't work, we'll move on. So trapezoidal rule, really simple. It's just going to be I over our step, which is B minus A. So our step size, okay, times by F of A plus F of B divided by 2, right? And that's only for 2 points, okay? Trap rule for 2 points. Okay? Trap rule for multiple applications is going to be this. So multi, which is I, B minus A, F of X0 plus 2 times f of all the other points, okay, plus the last point, all right, divided by the number of points. That's for multiple applications. Okay, Simpsons 1/3. 1/3. Really simple. It's actually not that bad. Okay, I'll just. Okay, I'll go through 3 points as well. So I equals the step size. Okay, and that's going to be multiplied by our first point plus 4 times our inside point plus our last point divided by 6. Okay, because there's 6 parts in there. Multiple applications. Okay, which is I equals B minus A times our first value plus 4 times all the odd numbers. So x of odds. So let's say we've got our x values are x0, x1, x2, x3, x4, x5. So since this is the first one, x0 is the first one, this is going to be our odd value, and this is going to be our even value. Does that make sense? Why it starts like that? Do we get it? So we've got odd, even, even. It's kind of inverted. I know that says 1, 2, 3, 4, and you think intuitively it's not that way, but it is. So f of odds plus 2 of f of evens. But you're all smart. I think you know that. I'm literally just preaching to the professionals right now. And that's going to be divided by 3n. Okay. Now, Simpsons 3/8, I think this is the one that we don't know. So 3/8 rule is I 3/8 is B minus A, so our step size, f of x0 plus 3 of x I. So this one is for the multiples of 3. Multis of 3. Plus 3 f of xi. And this is the others, the other middle values. And then plus f of xn. All of that divided by, pretty sure it's 8. Oh, okay. What we can do, we can just multiply that whole thing by 3 on 8. So what I mean by multiples of 3, so again, if we have our x values there, right? So this is our first. Okay. The thing with Simpsons 3/8, you're going to know to use Simpsons 3/8 in any question if your number of values is a multiple of 3. So 3, 6, 9, 12, if that's your number of points, use Simpsons 3/8. I don't think they tell you that. So if we go all the way to x6, sorry, so this is our first value, it doesn't count. This is a multiple of 3, and I think that's the only one you use. So if we go to 9 values, x7, x8, x9, right? This is the multiple of 3, and then this is your last value. Okay, did that make sense? I'm trying to go through this fast. I like losing people. Yep, good. Okay, that's the formula. That's the formula. Okay, that's that week. All right, week 5 is differentiation. Okay, this is differentiation by approximation. So who remembers first principles? Beautiful. So first principles, imagine that, but then imagine there's 6 different formulas that look exactly the same. Okay, and they're all based on previous x values. Actually, I was traumatized. Yeah, so there's actually how many? That's 6 times 6. So really there's 18 formulas, but you don't have to learn them. I'm pretty sure they give them to you if you need them. Actually, no, they did give it to us in the exam, didn't they? They gave us all of them, and we were F yeah, we were so happy. Anyways, so week 5. Okay, so what this is called, this is our backwards, forwards, and centered finite differences. Okay, so each backwards, forward, and centered have their own formulas. And basically what this means is that, like all our other questions where we had, where we had different xi values and then xi plus 1, these equations use xi plus 1, xi plus 2, and then also -1 and -2. So if we draw this on a plane, we're going to have xi plus 1, xi plus 2, and then like x minus 1, xi minus 2. And then you're going to like find their respective like f of x values. And then these are what the formulas look like. Forward finite difference formula. Okay. So they kind of look like this, but it's not that. Oh, okay, that's Runge Cutter. I don't want to like confuse you guys with like week 9 content. Yeah, they kind of look like that, but there's like more of them. Anyways, I'll just write the ones that we need for these like examples. So okay, so first derivative, right? So this is to find the first derivative. Second derivative has its own formulas. Third derivative has its own formulas, and then each one in backwards, forward, and centered has their own formulas for each of those first, second, and third derivatives that you're trying to find, like each approximation. You know what? I'm just going to show you guys like this. Okay, so can you see that? You see all those formulas? So like that's all the centered formulas. So like these two are to find first derivatives using the centered method, like first derivative for the backward method, and then first derivative for the forward method. Okay. I'll write down like one of the formulas and I'll explain to you all the notations. But it just looks like first principles. Like it's not actually that bad. That's all it looks like. It's not that bad. It's pretty good. I'm just trying to convince myself that it's not bad. I'm gonna cry. Yeah. Okay. I'll just do an example. So let's go with f of x equals minus 0.1 x to the 4 minus 0.15 x to the 3 minus 0.5 x to the 2 0.25 x plus 1.2. Okay, so you kind of need the exact you need the exact answer, like the exact first derivative to calculate for error. I'm just going to tell you what that is. So f dash x, right, for 0.5 is going to be negative 0.9125. We'll just save that for later. So you can actually calculate these using like normal differentiation, obviously, but we're just going to solve it by approximation just to show you how it works. So if we've got a step size between all of our x values, like I plus 1, I plus 2, minus 1, minus 2, of 0.25, we're going to end up with our centered value being 0.5, and then our -1, -2 is going to be these, and our +1, +2 is going to be this. Right, so that's our x -1, that's our xi, x plus 1, and then x plus 2. Okay, so right now I'm just preparing the question. Then our actual like f values, like our y values, so f of 0 is going to be 1.2, 1.103, 0.925, 0.636, and then 0.2 for the last one. Okay, so then we'll just practice using the forward finite difference. Oh man, I had a full Excel spreadsheet prepared there, but I don't think that's gonna happen. Anyways, that's fine. So I'm gonna use this formula. So this is now the forward finite difference. Like this is the forward method to find the first derivative. Okay, the formula is f dash x, which equals minus f of x plus 2, xi plus 2, right, plus 4 f of x plus 1 or xi plus 1, and then minus 3 f of xi. Okay, and all of that is over 2h, h being our step size, which is 0.25. So if we plug all those values in, right, so this one being this value, this one being this value, this one being this value, that's a 0.2, right, we're going to end up with a value which is negative 0.859376, right? And then if I use the error formula again, which is what I showed you guys before, can someone tell me what it is? Help me out here. Should I just write it again? I'm just going to write it again. So it's the absolute value. I think you started saying it, Farhan. So xi minus the exact, right, which is this one here. So f of x exact divided by f dash x exact times 100%. And basically, this formula, this method, right, gave us an error of 5.82% or something like that. Okay. The reason why I'm showing you this, if I was using my own laptop, I would have showed you all the formulas on a spreadsheet because I sort of pre-cooked it earlier this morning. Every formula, all of those 18 formulas has a different level of error. And it's really important to understand that because sometimes, well, the point of this question is that sometimes you're not going to have a function that you can actually derive. So you need to know which formula has the lowest amount of error that you can actually use so that you can appropriately pick an equation and you can sort of guess like, okay, I'll use this formula because it's got the lowest amount of error. Like I can accept that, you know, I'm only going to be 5.8% away from the true answer, right? Some of them have an error of like 26%. Okay, so that's why it's important to have so many formulas. And also, if we go back to here, this scale, for some functions, we're not given all the values. Like we're not given these. So if we're only given this point forward, we can't use the backwards finite formula because the backwards finite formula uses x minus 1, x minus 2. You know what I mean? But in contrast, if we only had xi and then, I plus 1, if we only had these three values, we can't use forwards or backwards. We have to use centered because centered uses the left and right values. See what I mean? Like, yeah, anyways, does that make sense? Why there's so many formulas?
If you had, so from xi, you had xi plus 1, I plus 2, and then also xi minus 1. Which one would you use?
Well, okay, that's a good question. So this is where it comes back to that idea where all the formulas have different level of like margin of error, okay? And also you can use different formulas for one scenario and you're gonna find that some of them you can't use because they use values you don't have and some of them you can use because they use values you do have. So what you do, you rule out the formulas that you can't use. So any of them that use, for example, x plus 2, since it's not there, you can't use it. So you already can't use the forward finite difference for the second order. You can't use it, but you can use everything else. So now you have to pick the one with the lowest margin of error. I wish I could bring up all the formulas so I can show you what I mean. But does that make sense? Yep. Okay. Beautiful. That's week 5. Okay, that's as far as I was going to go anyway. And I think that took me an hour. Did anyone die? I think a lot of people left. How are we feeling? Does anyone have any questions about the course? Week 7 to 10 is the same. It just builds on all of everything I just said. Okay, so it talks about what is it? ODEs. What does it stand for? Ordinary differential equations. So it's kind of like solving equations simultaneously, but in like 3 dimensions. And you need to like approximate. Anyways, I'm gonna stop talking. Thanks, guys. That was great. Yes. You're only going to use MATLAB. You're only going to use. You can do it by hand. Don't do it by hand. Don't learn MATLAB. Trust me, learn that MATLAB. let's all work together to help each other. I'm going to be doing the course with you guys. I know I wasn't like a god at this explaining it to you, but that's because the last time I did this was a year ago, and this was me in the last week trying to learn all the content ahead of time again so I can share it with you guys. But I'm also doing the course with you, so we can work together.
What would you say is like the hardest part of the course?
The very end.
Very
So 7 to 9 are a bit rough, but it's so doable. It's really doable. Also, stats is hard, and that's Akshar's job.
I was gonna
so.
say we're not quite done yet. We're kind of 50% of the way through.
Sorry, I'm sorry.
Okay. So yeah, go for it.
Draw?
No, I should be fine.
Are you sure?
Yes, should be all good. Yay. Great. Guys, all of the crash, I should say it's like our last crash course of the day. And so like we have a couple of tutors in here. So Johnny did the 2002 one, Josh did 2101, and then we have Farhan and Kwang who did 1300. They all volunteered their time. They don't get paid or anything, so everything deserves a round of applause. Alright. So I know everyone's brain is really fried right now. I'm gonna try my best to make this as simple as possible. But it is statistics, so who knows if that's even possible. Alright, so I'm just gonna walk you through my notes that I used when I did the course. So if anyone wants access to these, you guys are welcome to have them. I have also Johnny's section of the course as well, like the numerics ones. I have notes there. There should be some MATLAB code included in those, so if you guys want access to that, you're welcome to come and talk to me, and I can DM you the Google Drive link. But in the meantime, we will look at weeks 1 to about 5 of the stats course. Okay, so the way the stats course works is that it's all done on Mobius pretty much. The weeks get released at least, a week or so in advance, and then I personally preferred the way the stats course was structured because it just took you through like one lesson at a time. So like one Mobius lesson would be like one specific formula, and then it would move on throughout that topic like at a similar pace. So to start with, I'll just start with some revision of probability. So down here, I would say one of my biggest pieces of advice for the stats course is that just like remember the terminology that they use, because sometimes it gets thrown around a lot, and I kind of got lost when I did it because I couldn't remember exactly what they were talking about. So the way my notes work is that anything that's colored purple is probably like a key point or a key formula that you could take out of it, and then anything that's green was used specifically for your Mobius lessons. So hopefully if they like haven't changed anything, then it should be relatively similar. Okay, so over here is a bit of notation. Can everyone see like the highlighted purple box there? Okay, so we just have a bit of terminology here. So union means the event is either A or B, so only one of the two can occur. Intersection means both of them can occur. Complement just means that A doesn't occur, or like one of the events doesn't occur. There can be a situation where you've got this like little sideways curve, and that means one event implies that the other event happens. When you've got this circle with the line through it here, that kind of means that they're mutually exclusive, so one is not dependent on another. The word dependent is pretty important because you'll hear that get thrown around a lot, whether the events are independent of one another or whether they're dependent on one another. And yeah, so that's the notation. I'll just run through a quick example here from the Mobius exercise. Okay, so you survey 10 people and ask them if they think marijuana should be legalized, and an outcome is a set of 10 yes or no responses. So in this situation, do you reckon it's union or do you reckon it's intersection? What word do you think this? Yeah, it's intersection. Oh, jokes. It's union. Because nobody can say yes and no. So intersection means both of them can occur. Union means either yes or no, which is the situation here. So the first question is, how many possible outcomes are there? You might have remembered this if you guys did extension or advanced math in high school. You just use 2, which is the number of total options you can have. So it's either yes or no, which is most likely how a union event will work. And then you times it to the, you put it to the power of the number of like results taken. So basically, I guess if I quizzed everybody in this room, let's say there's around like 15 people, and I asked you if you were a fan of Cheezels, right? And you can only respond one of 2 ways, yes or no. What do you guys think would be the total number of outcomes in that situation? Yeah, exactly, right? Pretty easy, right? All right, moving on. Okay, question 2 gets a little bit more complicated. We're talking about how many ways could 4 people out of the 10 people asked answer yes. So that means for every combination, I'm looking at only the ones where 4 out of the 10 people have said, yes, I would like marijuana to be legalized, right? So the way that we do that is this formula here, and that's called conditional probability. So, hang on. Yeah. So you take the total number of results taken, and you use the factorial function, and then you put it over the outcome that you would like to occur, which is, in this case, what is it? What are we looking for? Sorry? Yeah, yes, right? We want to look for people that have said yes, and we only want them to be 4. So that's where the 4 factorial comes from, and then you just put the remainder in the bracket and you multiply them, and then 210 is your answer, right? Question 3 is where we look at probability. So before, we were looking at all of the total number of options, or we were looking at how many times an option can occur. Now we're looking at the probability that that option can occur, right? So it's the same situation. We're still looking for the options where 4 people have said yes. So this notation here is pretty common. It just means the probability that, whatever is happening has occurred. So again, a similar formula. You take the total number of outcomes that you found in part B, because that's how many times that 4 people can say yes, and then you just put it over the total number of options which you found in part 1. And then you just divide the 2, and that's your percentage, I guess. Or it'll be 0.21, and then you multiply by 100. Okay, does anyone have any questions about that kind of notation, anything at all? Right, great. Okay, so now we're kind of going to move on to week 1 and week 2, which is kind of using descriptive statistics. So we'll go through a quick example here, which is, I believe, from one of your labs. Okay, we won't go through all of it because we're running short on time, but let's quickly look at this one. So answer the following yes or no questions and explain your answer. Will the sample mean always correspond to one of the observations of the sample? The answer to that question is no. So it just depends on what you've got in your set here. So this is a very simplified question, but your data is basically your set of numbers. Your variability, that's also an important term, is a measure of how different your results are. So if you've got a set of 10 numbers and they all range between 1 and 3, that's a low variability. And then if you've got a set of 10 numbers that range from 1 to 100, that's quite a high variability. Make sense? Okay. So will exactly half of the observations in a sample always fall below the mean? So in high school, when you found the mean, that was the average, right? Was it dependent on the number of values that you had, or was it dependent on like the values themselves? Like what changed the mean? What influenced the mean? Yeah, the values themselves, right? So if I have a set of numbers, to give you an example, 10 values, and I have most of them ranging between 10 to 15, but then there's one that's like 100, right? That's a situation where the mean is completely influenced and it's going to drag the mean like above 15 probably, right? So it's not always guaranteed to fall like exactly halfway underneath the average. Does that all kind of make sense? Those statistics, everyone knows what mean, median, mode is. We don't need to go through that. Okay, great. Okay, week 2. This is kind of where it starts to get a bit complicated. So I would pay attention in this page to anything that I've highlighted kind of in the purple there, because those are kind of new terms that we didn't cover in like first year. So a random variable, something is a random variable when it's a real value defined over a sample space, right? And then your domain of variation basically is the set of all the possible values. So if I said that I was only looking at like positive integers, then the value or the domain of variation would be pretty much anything above 0. And then if it was the opposite, it would be anything below 0. Does that all make sense? That is denoted by SX. A lot of the time in your questions, you'll just get these random symbols and signs just thrown in there, SX being one of them. And you just have to remember what they mean. So a capital S usually means that you're talking about a set of values. So you're talking about all of the values that are possible in your experiment, right? So what can we do? The dice example, that one's good. So in this example here, for example, we're looking at the probability that x is equal to 2, which is 1 out of 36. So in the one underneath, we're looking at the probability that x is greater than or equal to 11, which is denoted by those squiggly brackets, and then all of the combinations that it could be inside. I would pay attention to how they're written, just because most of the time the brackets and everything, that's how you're going to input it into MATLAB. And with statistics, MATLAB was extremely helpful because it's just like one function that you throw in there and all is well. Okay. Okay, some more notation. If you've got, yes.
Why do you not need the brackets for the set 1?
The set 1-1.
For that type.
Because there's only one answer. So when you think about rolling 2 dice, there's only one possible way that you can get 2, which is 1 and 1, and then that's it. The other one, there was like more combinations, I think. Yeah. Any other questions? Okay. Yep, so just some more notation here. If you're talking about a capital X, they're most likely talking about the name of a random variable. And then once they include the brackets, they're talking about that specific random variable at a point. So if I said like capital X bracket 10, you're talking about the 10th number in your set, where X is the set. Does that make sense? Yep. Okay. Okay, cumulative distribution functions, they're defined for any real number x by that notation up there. It's probably better for me to explain it using like the graph or an example. Yeah, we can use this one. So electronic items independently have a probability, so P, that's important, of 0.1 of being defective. So before I move on, so we know that there's a probability of 0.1 that the item is defective. So what would you say the other option is, like the value of the other option? Yeah, because it always has to add to 1, right? Okay, so we're letting X be the number of defective items out of 2 that have been purchased, right? So the first question is find the probability that no more than 1 item is defective. So I kind of like this question because it kind of explains it really well. It wasn't always intuitive to me, but if you look at it, we're looking at the probability that X is less than or equal to 1, right? And the way that it's broken up is really nice. So because we're only looking for the probability that no more than 1 item is defective, it means we're looking for the probability that X is equal to 0 plus the probability that X is equal to 1, right? Because if if X is equal to 1, then you know that no more than 1 item is defective, and then if probability is equal to 0, then you know that more than 1 is defective. Does that make sense? Okay. So then once we know how to set it up, and once you've defined your equation, you can just use the values that we already know. So we take 0.9 times 0.9 plus the 0.1 times 0.9, and then again plus 0.9 times 0.1. Right, and that's the value there. Alternatively, you can take the total probability, which is always 1 in a cumulative or CDF, cumulative distribution function, and then you can minus the probability that it's talking about. So in this case, it's 0.1 times 0.1, which ends up being 0.99. Okay. All right, so some more examples here. Discrete random variables. Does anyone remember discrete random variables from first year probably? Yeah. So it's discrete if it can only assume a finite or countable infinite number of variables. So just like I've notated here, there's only a set number of values that it could be, and it won't go on forever, in other words. The probability mass function as well is pretty important. That's what we're dealing with here. You'll get taught what this is. This is taken from the lecture slides, so you'll be able to look at this in more detail. But probably the best way to explain this is by doing an example. So this is another 6-sided die. So the difference between the probability mass function and the cumulative distribution function is when you're dealing with a probability mass function, you're only dealing with that one event. So when you roll a dice, what is the probability that you're going to get any number between 1 to 6? So what's the probability that you get a 5? 1 over 6, right? Okay. And then when you roll a 6, it's the same. It'll be the same from the numbers 1 to 6. But the cumulative distribution function, you add the probability each time, and then it'll always equal to 1. So if you hear the word cumulative, it's usually a sign that it adds to 1, right? And you'll become very familiar with the graph, but it more or less looks the same. So if you've got an increasing graph that is, increasing every time you take a test or you take a survey or obtain any kind of result, then you're looking at a cumulative distribution function. And then if you're looking at something like this, it's just your probability mass function. Okay. Here's another example. So in this one, the probability mass function of X is this one here. So you know that the probability of a 0 is a 0.5, a 1 is a 0.25, a 2 is a 0.2, and then we're finding the value of C, right? So the PMFs, they always sum to 1. So the first question here, find the value of C so that fx is a PMF. You just take 1 minus all of your given probabilities. Makes sense? So then obviously our probability that the number is going to equal to 3 is equal to 0.1. And then here we're finding the probability that x is less than 1. So without looking at the working, how many options are we looking at? Yeah, exactly. So,
Greater than 1.
yeah, greater than 1. So it's 1 to 3. So here we've just got probability of x is equal to 2, probability of x is equal to 3, and then you add them both, and that's all. Here it's a bit more complicated. So you're finding the fx for all possible values of x. So you just have to work in intervals in this case. So the first interval is always the interval beyond the first value. So in this case, that's the one that's less than 0. We know that that's not a that's only a possibility in the first column, so it's given to us. It's like 0.45, right? That it's going to range between 0 to 1. We know that there's no value below 0, so that's a 0 there. So everything that I've written in like a brace format is the cumulative thing, and then everything on the left is just the probability of that specific row. So again here, if the number ranges between 1 to 2, we know that there's only a small possibility that that happens. So you go from 0.45 to 0.7, and then you go all the way up until you get 100% or 1. Any questions so far? I kind of went through that week pretty quickly. All right. So the opposite of discrete. So what did we say discrete was? We said that it was concerning probability values that are countable, right? So the opposite of discrete random variables are continuous random variables, and they're defined over an uncountable set of real numbers. Okay. A common way, how can I say this? Common continuous random variable. That's like any time you've got like a measured value, because you can have it in decimals, right? So there's no there's no set like number for each value. Like if I measured heights in this room, for example, to like the nearest like 3 decimal places, we can't always predict like what number it's going to be, right? So let me go down to another example. Okay, I don't have any examples about continuous random variables, but does everyone understand what they are? Okay. Yes? Fabulous. Okay, so I did want to go through this one quickly because I remember writing down the MATLAB function for it. So here we've got the 6-sided die again, and we're finding the expected value. Does everyone remember what an expected value is? Yeah, the mean, right? Okay, so this is kind of the way that you do it by hand. This is a very simple example here. In the case of discrete random variables, you can use this formula up there. So the x multiplied by the probability of that event occurring. And then with continuous random variables, you have to integrate them because, like I said, there's no way to count each variable. Okay. So if we go up here, remember anything that you see that's in green, I took from when I did the Mobius example. So this will probably come up at some point when you do like your week 2 stats lecture. So in this example, we've got we're looking for the expectation of an outcome when 6-sided dice is rolled. Like we said before, the probability of each event occurring is 1 out of 6. when you add all of them to, when you add the cumulative function together, you get 21 out of 6. Because in this case, fun fact, the distribution is symmetrical, you can actually take the median value. But if, we always won't be that lucky, so there will be many instances in which the probability isn't the same all throughout, which means you have to actually do the calculation. Okay. A situation like that is when you roll 2 dice at the same time, right? Because you're more likely to get some numbers than you are like some of the other ones. Like 1 and 12, you can only get them, or 2 and 12, you can only get them once, and then 1 you can't at all. So that is when you have to use the expected value formula. So on MATLAB, you can put it in like that. I'll just walk over here. But basically what this notation means is that you're dealing with numbers 1 to 6. Because on your dice you can only have numbers from 1 to 6 on them. And then from 5 to 1, you do in increments of -1 to make sure that you're taking into account every single number until you get to 1. Right, and then the expected value, this is just how I've notated it. You can notate it any way you want. You just sum all the possibilities up. This corresponds to that formula up there. And then remember to put it all over your total number of possibilities. So, yes?
Is that 2.12 or 2 times 12?
Good question. We can test it. Get rid of this. So we can put this code into MATLAB here. So if there's something wrong with my notation, please let me know. I'm kind of a bit rusty with it. Yep. Okay. Okay, so x turned out to be 24, so it's 2 times 12. Yeah. Oh. I guess I didn't write it down, but it would be the expected value because it's like it would be like somewhere between 1 and 36, right?
Yeah. Okay.
Yeah.
That actually makes sense.
Okay. Okay, so in this particular example, we delved a little bit into Bernoulli variable, and Bernoulli's is kind of special because the values or the results can only be like 1 or 0. In this case, we're dealing with a coin toss where the probability pi of landing heads. So in this case, you just let x equal to 1, and that would be like your successful variable, I guess, and then 0 is tails, which is your 0. And then the expected variable, which will always be the same in most Bernoulli questions, is just the probability, which they've defined as pi, multiplied by the successful value, plus 0 multiplied by whatever's left, which is 1 minus pi, in other words. Does that Bernoulli example make sense? Yep. Okay. This is more or less the same thing. How much time have I got left? I don't have that much time. We'll probably move on to we'll move on to special variables because this in the exam was kind of the easiest way to get marks because you just, depending on what function you're using, you throw them into MATLAB and then it just gives you the answer. So there are 3 special variables that we look at in stats. This is week 3, by the way, in case anyone missed it. The first one is the binomial distribution, which I'm sure you guys have heard of at some point. The way that you throw that into MATLAB is this one, or this function here. So in this example, we took disks that were produced by a certain company where the probability of them being defective was 0.01. And they also give you information to say that they were independent of each other. So it didn't matter how many were defective. Each test was its own independently run test. The company sold the disks in packages of 10, so you know that your data set is, has size 10, and then it offers a money back guarantee if more than one of the disks are defective. So in this question, you were looking at what proportion of the package purchases can get their money back. So proportion is another important word. You'll hear that one get thrown around a lot as well. It's basically just another word for percentages. And they're looking for the percentage of the package that would be defective. So in this case, without looking at the working, what do you guys think the successful outcome would be if we're dealing with either defective or not defective? Yeah, so we let X be the faulty ones out of 10. So we're looking for the faulty ones. So that's our 1 value. So we know that the binomial out of 10 is equal to not the binomial, but when you're looking at the binomial out of the 10 functions, you know that the probability is 0.01, right? And then to find the probability that X is greater than 1, you take 1 minus the probability of the remainder. So in this case, that's whatever this is, approximately 0.0043. But you don't have to do all of that by hand. You can just throw that into MATLAB, where you take 1 minus the binary CDF. You take 1 because you're looking for anything or any package that has 1 or more defective pieces of disks, and then you take the total number in your set, which in this case is 10, and then you take the probability that one of them is defective, which is 0.01. Because you're looking for 1 defective disk. So as soon as it's defective, or as soon as there's 1 defective disk, they get their money back. Does that make sense? Yeah. You can see it in this example as well. So let 4 be the returned number. What does that say? Oh, y. Let y be the number of returned disks out of 3. And in this case, in MATLAB, you put 1, 3 because you're taking the test 3 times, and then you'll find, I guess. Oh no, you found it up there, 0.0043. Does that question make sense to everyone? Yeah?
I guess the hard part is going to step forward.
Yes. It actually depends on the question. So if you read the question really carefully, which is what I feel like a lot of people got caught out on it, because the question will give you hints as to what kind of situation you're looking at. So you know that in the question you're looking at defective disks, right? So you can't have a disk that's in between defective and not defective. It's either broken or it isn't. So you know that there's 2 possible outcomes, and so you're dealing with a binomial distribution. That's kind of a good segue into the next special distribution, which is the Poisson distribution. This is another special condition which they'll give it away in the question. So this one is modeling the number of occurrences over of some test over a set period of time. So the questions will be phrased a little bit like this. So over a 10-minute period, and then as soon as you read that, you should know that, oh, it's a Poisson distribution, if that makes sense, because you're measuring it over a certain period of time, right? So this example, over a 10-minute period, a counter records an average of 1.3 gamma particles per millisecond coming from a radioactive substance. To a good approximation, the distribution of the count, which is capital X, of gamma particles during the next millisecond is Poisson distributed. So they even told you in this question here, right? So in this case, we're finding the expected value. So here we let X be the number of particles in the next millisecond, which we found by multiplying. Oh, I don't actually know what I did here. It's given in the question. So it's your expected value. It's 1.3, which you didn't have to calculate. In this one, you're determining the probability of observing one or more gamma particles during the next millisecond. So one or more. So it's the probability that X is greater than or equal to 1, which you find by doing 1 minus probability that is equal to 0. And you get 0.73. But this is all doing it by hand. You can do the same thing by using these commands here. So the Poisson CDF function on MATLAB, which we kind of did in this question here. So suppose that the number of kangaroos killed per week on a particular stretch of road has a Poisson distribution. Again, they kind of told you what function to use. And they gave you the average of 20 per week. This is kind of embarrassing, but I don't know what that Greek letter is. Yeah, lambda, that's it. So it always, with these questions, that one kind of means average, and that's another hint that you can use to determine which distribution it'll be. Like if it's denoted like that, then it's a pretty good guess that it'll be a Poisson's distribution. So yeah, in this case, you've got an average of 20 per week. I guess a tip is to always like write it like that or define your probability, because the X and the P notation is something that we're all like pretty familiar with. So if you want to, I guess, write it in terms that you'll better understand, it's better to just get it out of the way when you read the question. But in the first part, it's asking for, like, in the long run, what proportion of weeks will the number of dead kangaroos be? At most 10. So here we're looking for the probability that X is less than or equal to 10, which you can do really quickly instead of doing all of that by putting that into MATLAB. So the specific case that you're looking for is 10 when you know that the average is 20. So if I could write a formula for you to put in your notes or anything, I guess this will be like your X value, and then that value will be your lambda, in other words. So in this case, it was 0.0108. And then, what was this question? Part B was looking for numbers that exceeded 20. So again, probability X is greater than 20. You can either do it by hand, or you can do 1 minus 20, Poisson CDF 2020, which is 0.04409. So these special variables, they always just saved so much time in like quizzes and stuff, because as soon as you know which one to use, you just plug it into MATLAB and then you'll finish. But does anyone have any questions about week 3? Does everyone remember like when to use the binomial distribution and then when to use Poisson distribution? Can anyone tell me what they are? So binomial distribution is kind of in the name. So if you've got 2 options, right? Use the binomial distribution, which is the bino CDF function here, or bino PDF function, depending on what they're looking for. And then Poisson CDF, what was the hint that they kind of gave in the question? Sorry? Yeah, they did tell you in these 2 questions that you needed to use Poisson CDF, or it was a Poisson distribution. But the important thing to know about Poisson is that it's always set over a period of time. So if they start talking about like years, minutes, hours, then that could be like a flag for you to pick up on. Any other questions about special variables? No. Okay. I don't know if I have time to go into week 4, just because we've got 4 minutes left. But you guys are welcome to take these notes. I am happy to share them, so please let me know, and you can DM me with any questions, but I'm happy to wrap it up there. Yeah. That's all.
Thank you.
That's all right.